All right, so let me begin with the scripture here. It's Romans chapter 12, verse 3, actually. For through the grace given to me, I say to everyone among you, not to think more highly of himself than he ought to think, but to think so as to have sound judgment, as God has allotted to each a measure of faith. For just as we have many members in one body, and all members do not have the same function, so we, who are many, are one body in Christ, and individually members of one another. That's Romans chapter 12, verses 3, 4, and 5, I think. So I'll begin with a word of prayer. Heavenly Father, we thank you again for this opportunity we have just to meet together and study your creation. Just pray that you'd, again, be glorified in what we do, and that we all understand a little bit more about differentiation today, Lord. In your name I pray, Lord Jesus. Amen. All right, so this issue is always with us. Let's see if we've got it this time. Well, I got a 2, and I will admit, as I look at this, I'm like, wait a minute, is that 2 cubed, or is that, but you chose rightly. I meant to say cube root. If you're unsure whether it's like a 2 cubed or a root 2, I think it's more clear in the typeset mathematics, right? But if you're ever in doubt about where the 3 goes, ask me, all right? But it goes on it's a cube root. And so, I like the half out here is fine. That 2 is 2. The cube root of 27 is 3. But if we have the cube root of 27 times x to the power 5, we can do like this. It's the cube root of 27 times the cube root. The cube root of a product is the product of the cube roots. That is true. So what we should have there is like a 3x to the 5 thirds. But I guess you do have that, but why? No. But you want to write this, because I don't know what. I'm okay. I'm going to erase. I'm not saying it's wrong, but yeah, I'm saying it's wrong. What I mean to say is I'm not sure if it's wrong. What follows, I just know it's not the right way to do it. Does that make sense? So it's not wrong, but it's not right. Because what we want here, so generally as a point of order, if you're differentiating something, it is worth your time to algebraically simplify it before you take the derivative. So in this case, we have the derivative with respect to x of, let me throw this thing out, it's a piece of trash. There we go. It's like a layup. Let's see here. 2 times 3 is also known as 6. So you've got 6 x to the what? X to the 5 thirds. Okay? First order of business, clean it up. Then differentiate. So that is nothing more than 6x to the 5 thirds. Although I forgot something. What have I forgotten? The 1/2, right? That's square root. I need to take my own advice and not forget the overarching square root. All right, so let's try this again. That is d dx of the square root of 6 times x to the what? What's the square root of x to the 5 thirds? That is equal to x to the 5 thirds to the 1/2 power, right? So that gives us 5/6. Now we can differentiate, right? Pull the square root of 6 out because that's property of the derivative, and then power rule. So I get 5/6. X to the, what is 5/6 minus 1? It is minus 1/6. There you go. Now you could simplify that answer a little bit. Like you could also write this, say, as 5 divided by, the square root of 6x if you wanted. But or you could write it as 5 over, the square root of 6 times the square root of x if you wanted. I mean, any of these would be fine. Any questions about that? Good. All right, I'm gonna have to zoom in on that. Let's see here. We have chosen the font of a smaller room here, which is good. That's fine. I'll get it. All right, there we go. I'm not saying it's wrong or right because I can't see it until I get here. What we got? Chain 1, tanh theta, where wait a minute. Okay, the derivative of tanh is hyperbolic secant squared, agree. So the derivative of that function is hyperbolic secant squared times c. Very good. Product rule you don't need here because a is a constant, so there's no need for product there. Derivative of sinh is cosh. So this is the answer?
Yeah, but
The potential answer, but you know it's wrong? Okay, cool. So cosh of A tanh of B plus C theta, that's good. That's definitely part of it. And then multiply by C
that should just be
A. Yeah, tell you what, I'm going to just, it's hard for, I'm very gullible, so I'll be sucked into your mistake if you made one. Let me just go ahead and differentiate here. Let me call this thing, I'm going to call that thing y and just put dy d theta down here, and then we can compare what I get to like what you got there. So, all right. So sometimes when I'm differentiating something that's got like an onion, it actually makes a nicer answer if you do the most inner derivative first, and then times the derivative of the next thing, and then times finally. We never write the rule that way, but like in terms of practice, so like the most inner derivative is c. And then the derivative of the next thing would be a hyperbolic secant squared of b plus c theta. And then finally cosh of a tanh of b plus c theta. That, I think, would be the answer here. Very good. All you're missing. So you almost, yeah, it's just like, there you go. So now it's correct. But yeah, great, very good. All right, next up here, example 3. We're supposed to find, so this is an implicit differentiation problem. All right. So let's see how that goes. Zoom out a bit. Let's see here. All right. Okay, so next up here, with implicit differentiation, what you do is you differentiate the given equation and let's say product rule. Not quite. This over here is good. Like the derivative of x plus y is y plus y prime. That's true. But when I differentiate, it's like when I differentiate this side here, what I should get is secant squared of xy times the derivative with respect to x of xy. Now maybe that's what you did though. So let me not be too critical here yet. Y plus dy dx. We might not be in disagreement here. Let me look. Oh, okay, yeah. It's fine. When I think product rule, I'm thinking of like the first rule you're doing is the product rule, but it's not the first rule that's the product. The first rule is the chain rule, and then after the chain rule, you're hitting the product here. But of course, we're going to get x times secant squared xy. Yeah, we get, so the product rule here gives us x times secant squared of xy times dy dx plus y secant squared of xy equals to 1 plus dy dx. Now solve for dy dx, we got what? I think this is right. I don't really need to rewrite this. So yeah, you got it. Woohoo! Very good. Yep. So all that's been done here is just put the dy dx both on the same side, so you get x squared x times secant squared xy minus 1. And then on the other side, you've got 1 minus y secant squared xy, and then you divide. So, yeah. I guess I can include one more step here because I know some people will be lost on that step not being included. So I'll write that step down. And then one more step, just divide. It gets us to that answer right there. All right, so to recap, implicit differentiation, you want to find dy dx for, and so why do we have to implicitly differentiation? Like, why are we doing this? Well, can you solve for y? Right, you simply don't have the option to solve for y as a single function of x, right? X and y are somehow like intertwingled, to use a technical term, by that equation, right? They're intertwined by this relation here. So advanced calculus says implicitly, like at least locally, there's a way to write y as a function of x, all right? Now I can't really describe to you what that condition is. Just rest assured that is possible. And because it's possible, it's not a fool's errand to calculate dy dx, at least in the context of the theorem that I can't state in here. So, but that's how we roll. So next up here, via log differentiation. So I believe this is a good faith effort for log differentiation. We took the natural log of the equation. We've got natural log of y is 3 log of sine x, very good, from that term, plus 3, because of this 3 right here, log of x squared plus 5, very good. And then minus 1/2 log x, excellent, because this is a square root in the denominator, which brings out a minus 1/2 power, all right? And then you differentiate with respect to x, both sides. We get the chain rule here. 1 over y dy dx is it was going well to that step, but that's good. It's good, it's good, it's good. I can fix it. So the starting point is good. The 1 over y dy dx is good. But I've erased it. My apologies. So differentiating this, we have 1 over y dy dx is equal to 3 cosine of x over sine x plus 6x over x squared plus 5 minus 1 over 2x. The rule I'm using to form those differentiations is the chain rule for the log, which looks like this. d dx of the natural log of u is equal to du dx upstairs divided by u. So I use that chain rule over and over again in my log differentiation. And then finishing move here, dy dx equals to, let's make that a 3 cotangent x, because cotangent x doesn't get enough love in here. So cotangent of x plus 6x over x squared plus 5 minus 1 over 2 times big X, parentheses, that monstrosity, sine cubed of x times x squared plus 5 cubed, all divided by a square root of x. There you go. That is the technique of logarithmic differentiation. The technique of logarithmic differentiation is like a 3 or 4 step process. Step number 1 is to take the natural log of the expression that you're dealing with. Step number 2 is to apply properties of logarithms to separate the log of a product or quotient as a sum of logs and difference of logs is appropriate. All right. I put this all into one big overarching step by giving you that like Uber lemma that we wrote last time, so we could just do it all sort of Machiavellian calculation, all our evil all at once, like you did right here. Wonderful. And then we differentiate using the chain rule for logarithms. And then final step, solve for dy dx. There is technically another possible starting step, which is to make sure you're taking the natural log of something that's positive. There do exist sneaky problems which tempt you to do logarithmic differentiation where you cannot do it. The place you cannot do it is when you're dealing with something which is manifestly negative. If something's negative, you can't take the natural log of it. But on the other hand, if something is definitely negative, it's easy enough to make it positive. You just multiply by -1, right? But anyway, I don't know if I have any examples like that to show you today. I'll save it for the test. Oh, I'm sorry, is that too soon? Here, I'll behave. Let me stop joking about your test. Although there is a test upcoming. It's not too long from now. All right, what we got here? So opening move, we took the natural log of both sides. Very good. So you got like minus x natural log of e plus 2. Oops. All right, I'm going to leave this because I want to talk about what's wrong about it. All right, so, but unfortunately, because it's wrong, what follows is not correct. Although I do think it does look to me. Oh no, it's not good. It's not good. All right, so let's just not. Yeah, no, sorry. All right, so let me fix this up here. So we take the natural log of y. That's fine. You got that. And I'm going to include one extra step in here just to emphasize what's going on. Natural log of e to the minus x. Great. And then we've got, oops. So I'm going to write out a step this time. I'm not going to use my lemma, just to sort of emphasize what's going on here. Plus the natural log of the cosine of x. And cosine squared is actually cosine of x squared, right? And then we have minus the natural log of 2 to the 3x, and then minus the natural log of the sine of x cubed. Notice there's a very big difference between cosine squared of x and sine of x cubed. That square means the whole cosine's being squared. The cube just applies to the argument inside the sign, right? They're really different. And unfortunately, look at this. I fished you in. See that? This would be the kind of thing you would do if we had like a sine cubed of x. You'd be doing that step. That's still not, there's something else wrong, right? It should also have a natural log on the sine. So like the next step here, I don't like this one. All right, so this is minus x. Natural log of e to the something, these are inverse functions. So like, this isn't wrong, but it's also not quite right, because you can simplify natural log of e. Natural log of e is 1. So there's no need to write natural log of e. We should just like write minus x for that term. This right here, you're almost right, but you lost your log. So don't lose your log. So natural log of cosine x here. And this one is just minus 3x natural log of 2. And this is what it is. There's really nothing more to do there except write it again. All right? At this point, we have taken the natural log of both sides. We have it nice and pretty. Now what do? Differentiate implicitly with respect to x. I mean, I say differentiate implicitly, but the truth of the matter is that we're talking about a, sorry, I haven't hit you yet. I did make a student duck in the other class. 1 over y dy dx. I wasn't really going to hit them though. I mean, not on purpose. Let's see here, plus, minus, because the derivative of cosine is minus sine, and I divide by my cosine. And then here I've just got minus 3 log 2. And then this guy, minus 3x squared cosine of x cubed divided by the sine of x cubed. So what's going on there is my inside function is sine of x cubed, right? The derivative of sine of x cubed is 3x squared cosine of x cubed by the chain rule. So my du dx on top of the 1 over u is that 3x squared cosine x cubed. The minus is there from the algebra before. And okay, so here we go. dy dx equal to, let me do a little, you guys tell me, what's sine over cosine? I can rewrite that as what? 2 tangent of x, yeah, that's not a bad thing to do. Minus 3 natural log of 2. And what's this? I could write that as, yeah, cotangent of what? X what? X cubed, very good. You're like, well, if I just write that as cosine over sine and sine over cosine, are you going to take points off? No, I would not. I am merely trying to teach you guys what tangent and cotangent is in this example, all right? The more times I talk about that, the more likelihood there is that more of you will know it, right? So that's what I'm doing. And then I have to write y again. So sometimes if I'm feeling nice, I say you can write your answer partly in terms of y. But I sometimes don't say that because it confuses students. So I'm just going to write it. All right, 2 to the 3x sine. Now, for the implicit differentiation problems, guys, the answer can include y. I should mention that. Did you notice that? Like if you go back to example 3, notice that the answer involved y. That's okay. That's almost inevitable for interesting implicit differentiation problems. The answer will involve both x and y. And that's okay. That will happen. Example 6. What do we got here? Differentiate now, right? So we differentiate. We got what? 1 over y dy dx equals to minus 2x plus 4x divided by x squared plus 1. You guys tell me why there's a 4 there while I'm adjusting the camera here. Why is there a 4 there? And why is there an x there? What's that about? The x squared, we differentiate the x squared, right? From the chain rule. And when we differentiate that x squared, what does it do? Yeah, I get that 2x. And that 2 times 2 gives me 4. So that's why there's a 4x there. It's the chain rule and the 2 that was there to start with by the algebra from the previous step. Next up, what we got? We've got ourselves a 3 times 3 is 9x squared because of the derivative of the inside function. So I got 9x squared divided by x cubed plus 1. And then finally 16x cubed divided by x to the 4th plus 1. I am repeatedly using this chain rule that I wrote over here in the corner, all right? This is the hero of this calculation. We use it again and again and again. All right. So then, solve for dy dx. What we got? dy dx equal to, apparently, and I'm not gonna try to simplify this, guys. So minus 2x plus 4x over x squared plus 1 plus 9x squared over x cubed plus 1 plus 16x cubed over x to the 4th plus 1. Close my big parenthesis, multiply by this. Y, either minus x squared. Why did I do this? X squared plus 1 squared, x cubed plus 1 cubed, x to the 4th plus 1 to the 4th. This is why it's important for the boards to be put next to each other. See, you can do that here. There's other classrooms where inexplicably they've put like 6 inches of wall between the whiteboards. That's not cool. It's like, why do you do that? Why do they do me like that? I'm tempted to go and like take like 6 inches of like the, you know, the slick bathroom. You can get whiteboard at Home Depot for like 20 bucks a sheet. It's not technically whiteboard, right? It's like bathroom paneling that's smooth and featureless and white, but those work as whiteboards pretty well. They'll hold up for a couple of years. I mean, I've used them in classrooms for several years. Vandals have come and installed them in classrooms that don't have enough board space for me, weirdly enough, but because of course I would have to ask permission from buildings and maintenance and stuff to put up a board, but well, who am I to say if a vandal comes and puts a board up for me? My brother's colleagues have a similar problem at Appalachian. They had a vandal come in and install flooring in their office one weekend, which was really nice for them because they happened to be allergic to carpet, which was in their office, but the hardwood floor that was put down afterwards was much better for their allergies. Very considerate vandals. Yes?
I was going to say I redid number 7.
You redid number 7? But you checked this on Mathway?
It said it couldn't even solve the problem.
Oh, it couldn't even solve the problem. Oh, yeah. That's because Mathway doesn't know logarithmic differentiation. But
I clicked on the calculator version.
yeah, but this is good. So on the test, I will have, there's going to be some problem on the test. It's like, here's an expression, use logarithmic differentiation to find the derivative. And so by that, I mean use logarithmic differentiation to find the derivative, which means you take the natural log, then you use the properties log, simplify it, you differentiate that, and then we do what we've just been doing in the last 3 examples, all right? So if you do this, on the one hand, I'm impressed because great, you know differentiation really well. That's good. But also, it's not following instructions. So I will take off points because the whole point of the problem on the test is to see whether or not you have learned the technique of logarithmic differentiation so that you don't suffer my fate and not be able to play and instead be stuck doing homework rather than practicing your Led Zeppelin. Although I don't play the guitar, so it's kind of irrelevant. So I'm so sorry to erase all this, but yeah. But thank you for doing this because it did serve a purpose for me to tell everyone that, which is something that needs to be said, so it is good that it was said. Now let's see if I do exactly, so you tell me what I'm about to do, if it's the same as what you did. So we take the natural log of both the expression, we got natural log of y is 2 natural log of x plus 1 plus the square root of x minus 2 times the natural log of x plus 2 minus the natural log of the sine of x. Now, there's something I did there that I haven't really explained. Why is it just square root of x? Like, what's going on there? What's that coming from? We'd have natural log of e to the square root of x, right? It's just what? It's just the square root of x. So there's that. Another thing that'll weird you guys out on a test question or something for some reason is if I inadvertently put a natural log into the problem. Like, that'll mess you up. Do you want me to put that? Let me put that into this problem. Here, let me add a natural log to this. Let's look at that because I haven't. I inevitably test on that, and I don't mean to be a meanie, but what if you had natural log of tangent? Yes, you can. And so that would just do plus ln of tangent. See, that's the thing, is like that question you just had, that will stop some people on the test from, they just talk themselves out of it. But yes, logically, that's what happens, log of log. Now we differentiate. So differentiating this goes how? Well, 1 over y, dy dx, and then we get 2 over x plus 1, plus 1 over 2 times the square root of x, because that's the derivative of the square root, minus 2 over x plus 2, minus the cosine of x over the sine of x. And now we're to my weirdo log term, right? We got to think through the chain rule. The inside function is log, right? So chain rule here looks like this. 1 over log of the tangent, but now I have to multiply by the derivative of the inside function, log of tangent, right? What's that? That is 1 over tangent right? But I have to multiply by the derivative of tangent as well, be the chain rule. So I have a secant squared. You put that upstairs here, secant squared, like that. And so that's what it is. And then dy dx. This is making me tired. Dy dx is equal to 2 over x plus 1 minus 1 over 2 squared of x. But I guess I do get paid for this. Let me stop complaining. All right, 2 over x plus 2. And the other thing about this is pretty much the only context in life that you can have like a conversation with people about math and not have them leave the room after about like 10 minutes. Like this is the sole context where most folks will tolerate you talking about mathematics for longer than about 10 minutes, in my experience. So there's that. And they pay you for it. It's pretty good. And then I have to multiply by y. X plus 1 squared e to the square root of x, log of the tangent, divided by x plus 2 squared, sine of x. There you go. So don't be scared of the log. You just take the log of the log and deal with it. Yep.
How did the symbol change for the 1 over 2 square root of x?
What have I done?
It went from plus to minus.
Oh, yeah, that's not good. When did I do that? Just the final step? All right, so let's fix that. Still in the marker. There you go. Thank you. Other questions? All right, I believe this next one's correct. I'm optimistic this one's correct, so I don't have to write anything because I'm tired. One thing I probably should tell you guys is like these are homework problems. Yeah. And by that I actually mean the ones I'm collecting. So I think I've assigned you guys like 5. Aw man, I hadn't moved the camera. That's a bummer. Sorry, people at home. So I think I've assigned like 5 logarithmic differentiations in mission 5 that I'm collecting. And those are 3 of them, maybe 4 of them. I changed that last problem by adding the log though, so you'll have to kind of interpret. I think you can see if I hadn't multiplied by the log of the tangent, you see that this problem would have. You can pretty much see the solution, right? To this problem, if I take away the log of tangent, what happens? It just kind of blanks out this piece and this piece and this piece, right? And that piece. All right, so here we go. Equals, ooh, yeah. I prefer to see d dx of x to the 4th plus y cubed minus y squared equals to dx. That would be kind of more, I'm going to just kind of lightly go, not quite right. All right, but with that picking this aside, I think what's right, I think what follows is right. 4x cubed plus 3y squared dy dx minus 2y dy dx equals to 1. Great. And then the next step, you subtracted the 4x cubed to the other side. Great. And you kept those there. Now you factored out the dy dx, and that left you with a 3y squared minus 2y. Cool. And then you divide by the multiplier of dy dx. We get 1 minus 4x cubed over 3y minus 2y. I'm going to rewrite that down here. So what you found is that dy dx is equal to 1 minus 4x cubed divided by 3y minus, that can't be right.
That would be 3y squared.
Yeah, 3y squared minus 2y. So you had the y squared. It was here. See, it was here. It was here. And then right here, it disappeared. I don't think that's going to make your answer wrong, though. because we're at the point 1, 1, so 1 and 1 squared, I don't think it's going to change anything with what follows, except that technically it's 1 squared here. All right, so then to find the slope of the tangent line, we plug the point into dy dx. So what is dy dx at the point 1, 1? All that means is put y equals to, so you got 1 minus 4 over 3 minus 2, also known as minus 3 is the slope. And then if the point is 1, 1, we can use our point slope, and we get 1 minus 3 times x minus 1 as the equation for the tangent line, which I think is what you got. Yep, cool, yep. Very good. Problem 216 from mission 5. Let me read you the story time here. It's a word problem. If I can find it. All right. The volume of a sphere of radius r is given by v is equal to 4/3 pi r cubed. All right. We might derive that at the end of the semester this semester, actually, if we get our ducks in a row and do. I think we calculate volumes in here, so we can calculate the volume of a sphere at the end of the course. I think it's within our powers. And all right. So you got the volume, you got a sphere, volume 4/3 pi r cubed. If a spherical balloon with radius of 2 foot is being inflated at a rate of 3 cubic feet per minute, then what's the rate at which the radius of the balloon increases? So, very good. We've got our v is 4/3 pi r cubed. The what?
On the far right side, the dr dt.
Uh-huh.
The 3 feet cubed per minute.
Oh. Right. But no, this is helpful. So, so far so good. Like, the volume is related to the radius like this. So we differentiate it implicitly, assuming the volume is a function of time, the radius is a function of time. And so we relate the rates. I'll just write it down here bigger. dv dt is 4 pi r squared dr dt. Very good. Then the question is interpretation. So problem 216 says that it's being inflated at a rate of 3 cubic feet per minute. So I was hurrying you. So you guessed it was 3 cubic feet per minute. But we can understand that that's wrong through something called dimensional analysis. So what's dimensional analysis? It says that variables should match their units essentially. So dr dt is a velocity, it's a rate. So it should have like feet per minute. But this is feet cubed per minute. And that's the kind of units we should have on volume, right? So this is not dr dt, it's actually dv dt. That's what we're given. We're given dv dt is 3 cubic feet per minute when r is equal to 2 feet, right? So all you got to do is solve for dr dt, which is dv dt divided by 4 pi r squared, which is going to give us 3 cubic feet per minute divided by 4 times pi times 2 feet squared, right? So like apparently 3 over 16 pi feet per minute. Notice that the feet cubed and the feet squareds reduce to feet per minute. And if you get a calculator, you can give me that as a decimal, right? If you're in my physics class and you leave the answer like that, I'm going to take points off. If you're in here, I'd be content with it. All right. I don't like this as an answer. I do want the answers to be like at least finish the arithmetic. Yeah. In here. Example 10. Ew. This is not bad, but you can't just add it. You have to like divide and conquer. So let's call it z. Z is equal to x to the cosine of x squared. Then that will give us the log of z is equal to the log of x to the cosine of x squared, which give us cosine of x squared times the log of x. Then differentiating, I get 1 over z times dz dx is equal to, minus 2x sine of x squared log x plus the cosine of x squared over x. That's the product rule. I'll get out of the way here in a second, guys. dz dx is equal to minus 2x sine of x squared log of x plus the cosine of x squared divided by x, parentheses, times x to the cosine of x squared. So that's how to differentiate half of this. The other half, we need to know what's the derivative of inverse cotangent. So you're going down the right path, but you can't just like, you got to like divide it. You got to separate it off and do half of it one way and half of it the other way. This problem requires a divide and conquer approach, because you really need to use different techniques to do the different parts. Is the thing, right? Now, if you guys already know the derivative of inverse cotangent, then great, you can just use it. But do you know it? I think it's minus 1 over 1 plus x squared, but I'm not sure. It might be 1 over 1 plus x squared. Let's work it out. So to work that out, I need some more board space. I'm going to erase this bit over here, if that's okay with you guys. Oi. So let's just say W is equal to inverse cotangent of x. I'm just going to like do that. Then that means cotangent of W is equal to x, which tells me that minus cosecant squared of W times dw dx is equal to 1, where I'm differentiating implicitly. The derivative of cotangent is minus cosecant squared. I think we did that another day. I could be wrong. Now that gives me that dw dx is equal to minus 1 over cosecant squared w. Now the question is, what's the deal with cosecant squared? Well, I go back to sine squared plus cosine squared, because that's my happy place. Right? Sine squared plus cosine squared is 1. How do I get the cosecant? I should divide by, cosecant's 1 over sine, right? So if I want a 1 over sine formula, I should divide by sine squared. Dividing this by sine squared gives me cotangent squared w plus 1 is equal to cosecant squared w. Aha! So apparently, and by the way, cotangent w is x. So this is literally x squared plus 1 here. So we get minus 1. Oh, I guess I did remember right. It's minus 1 over x squared plus 1. There you go. That's the derivative of inverse cotangent. Annoyingly, I put a 2 here, right? So what's the answer? So dy dx is equal to the dz dx I just found down there, plus minus 1 over 1 plus 2x squared times d dx of 2x. So here I'm doing the chain rule for the inverse cotangent using the derivative we just derived. Right? So x has to be replaced by 2x. This is a lot like one of the last ones I had on the quiz. So it's this mess down here, minus 2x sine of x squared natural log of x plus the cosine of x squared divided by x times x to the cosine of x squared minus 2x over 1 plus 4x squared. There you go. That would be dy dx. This is a challenge problem. All right? Because even an A student who knows full well how to differentiate the first term and differentiate the second term, in the heat of battle on the test, might not have the simple thought, oh, I need to break this up and calculate the derivative of the left term and the right term separately and then add those together, right? Because if you just try to take the natural log of this equation, that doesn't work. Like the natural log of a sum is enough. It's not anything. You're just stuck. You can't simplify it like that. Boy. Whew. Goodness gracious. I thought you guys were supposed to do the work today. Why I'm so tired. So, next up. Let me tell you where we're going. Tomorrow, I'm going to teach you guys about something called the linearization and Newton's method. And what that's about is simply, I hope I had that in frame, I don't know. What that's about is basically just going back to the tangent line idea, but thinking of the function whose graph is the tangent line and doing things with that. So anyway, we'll talk about that tomorrow. What's that?
Did you already fix the announcement?
Oh yeah, the announcement's fixed.